Thôi này đâu căng này.
Okay, good afternoon. Mr. Purin, can you hear me? Pirun, can you hear me? Sinara, David, can you hear me?
Did you call me, sir?
Yeah, can you hear me?
Yes, sir. Yes.
Okay, so you can see my screen, right?
Yes, sir.
Okay, guys, good to see you again. I hope you're all doing well. So we had to cancel this week's class on Tuesday due to some, what is it, guest, let's say, from the ministry. Anyway, so I'll try to compensate, and we're getting close to our midterm week, but we will see. Okay, not next week, but after next week, most probably you will have a midterm. That means that you will have midterm on December 30. Okay, but I will confirm this next week. So most probably, guys, on December 30 you will have a midterm. Okay, most probably. Okay, last time we talked about double and iterated integrals over rectangles. That means rectangular regions. Okay, but today we'll just generalize this idea to any region in the XY plane. Of course, not any region, but let's say most of the regions, because sometimes if the corners of the region, the integrating region is like fractals, for example, it may be some kind of troublesome. And that's why usually here in this book, okay, the regions that we're talking about is maybe rectangle or triangle or circular, okay, this kind of regions. That means that actually the size may be straight line or curve, which is a part of the circle. So what are we going to study here? Double integrals over bounded non-rectangular regions and volumes. Fubini's theorem, stronger form. The first form we have already studied in the previous class, finding limits of integration and properties of double integrals. That's what we are going to cover in this section, okay? And hopefully I'll try to cover everything in 35 minutes. After that, we have a short break, and then we have another section, and that's 15.3. That's all for today. And the cluster will continue with all polar coordinates. Anyway, guys, as I told you, repeatedly tell you, if you really understand the main idea about what is this, the definite integral for a function of single variable, right? And also here, the similar idea, we're just expanding this, okay? So if you remember, when we define a definite integral for a function of single variable, right, over the closed interval AB. How did we define this? We just divided that interval into small subintervals, let's say n subintervals. After that, from each interval by subinterval, we just pick one point and evaluate the value of the function at that point and multiply this by the width of this subinterval, which gives us the area of this thin integral, I mean the rectangle. So is our improve our partitioning, right? Which means that the number of subintervals gets bigger and bigger, which means that our n goes to infinity. That's double actually definite integral gives us the area which is bounded by the lines x equals a and x equals b. So let me just draw this to visualize the thing. So we are talking about some kind of function here. This one is, let's say this a, and this point is, it is b, right? We just divided this into small subintervals, right? So in similar way, suppose that now here we are given a general region, okay, which is bounded by some kind of curve, as you see in the picture by blue line. So in similar way, we'll just partition this region into smaller grids. That means that by drawing a lot of horizontal lines and the vertical lines, right? Actually, it forms a lot of small rectangles inside this region. Okay, but some at the corners, maybe they are not rectangles, but we are just considering all the rectangles inside this region. And after that, we form our Riemann sum. Here, this S of n, that's our Riemann sum, the K, because suppose that I just number these regions in certain order. Actually, the order does not matter how you number this. Maybe this one is our first rectangle, the second one, and third one, and fourth, and fifth, and sixth, and seventh, blah, blah, blah. So suppose that we just divide this into some parts, and we have n rectangles inside this region. And after that, we form the Riemann sum. How do you form this? We just pick one point from this one grid, right, and multiply the value of the function at this point by this area, that is delta A sub k. Since it is rectangular, our delta sub k is equal to delta xk times delta yk. And after that, it's just sum up all of this, right? We form a Riemann sum, because Riemann, the first time, actually, he discovered this or suggested this, and it's based on the area. That's why it's called the Riemann sum. And after that, if we evaluate its limit as this partitioning, actually the biggest rectangle's area goes to 0, which means that our n goes to infinity, right? So this sum approaches to some limiting value. So if this limit exists, then we are defining this as a double integral. That is double integral of f over the region R, okay? So dA. This is how we define the double integral over bounded and non-rectangular regions. So if our function is positive, for example, over this region, at the time, what do we get from this double integral? So this A of x, that's the area between G1 and G2x, because here our area is changing, right? At every line, if you draw a line, for example, the y is changing from different point to another point. For example, if you just move to the right, again, it enters the region at two different points, two different point, and exiting the region at, again, different point. That's why here, integration limits are the functions of x. They depend on x. So now if you just collect them, then this area, right, from A to B, if you remember from the application of definite integrals, it gives us a volume. So that is from A to B, to the second integral from G1 to G2, f of xy dy dx. Okay, now let's continue with this Frobenius theorem and immediately use this to solve one example. So it's the first form we have already seen in our previous class. Now this is the second or stronger form, that is for general region. It says that if we are given a function of two variables, f, x, y, and let it be continuous over this region R, okay, then if R is defined by this inequalities, a is less than or equal to x, x is less than or equal to b, and this y is changing from G1 to G2. And suppose we have two curves, right? Actually, this G1 is changing between these two curves. With G1 and G2 continuous on AB, then this double integral of f over r dA is just equal to, this is just showing us how to evaluate this integral from A to B, that is x is changing from A to B, and our y is a function of x, so that's changing from G1 of x to G2 of x. Okay, here we have f of x dy dx. Or also actually we can change the order of this integration. If R is defined by C less than or equal to y, less than or equal to d, and h1 of y less than or equal to x, less than or equal to h2y, with h1 and h2 continuous on CD. Then this double integral of f over r dA is equal to y is changing, this y is changing from C to D, right? And our x is changing from h1 of y, h2 of y. Okay. I will see this in examples immediately. Find the volume of the prism whose base is the triangle in the xy plane bounded by the x-axis and the lines y equals x and x equals y, and whose top lies in the plane. So we are talking about the prism here. Just write here solution, and that is sitting over this, what is it, triangle. So that's our x, this is y, and y equals x. This is our y equals x. X equals 1 is, it is this line. right? So this point is y, since the equation of this point is, the line is y equals x, so this intersection point is 1 and 1. Also, this one is 1, right? So this line, x equals 1 and x-axis, so we are talking about this region. So we are talking about this region. Okay, so we are integrating this. And from the top, actually, the top of this roof is lying in the plane f of xy equals 3 minus x minus y. Okay. So now we will calculate this in two different ways. Number one is, since actually over this interval, where our function is positive, which means that our double integral gives the volume of this solid, which is sitting on this triangle, and the top is covered by the plane, which is given by the equations 3 minus x minus y. Okay, so the first one is, let me just write here the first, change the color. So since it is volume, let me just use v for this. Integral. Now first, x is changing from 0 to 1. So from 0 to 1. And how about y? To find the integration limits or limits of integration for y, you need to draw a line that is parallel to the y-axis. If you just draw a line parallel to the y-axis, it enters the integration region here and exits here. So this entering part is, what is it? It is y is equal to 0. And how about exiting part? Actually here, y is equal to x. So that means that our y is changing from 0 to x. Let me use the same color here. Okay, here we have from 0 to x. So our function is 3 minus x minus y. And here we have dy, and here we have dx. Okay, that's it. And especially this integration limits, that's the most important thing, otherwise you'll get wrong answer. So equals, now you know how to evaluate this. First, starting from the innermost integral, so we have to integrate this 3 minus x minus y with respect to y. That means that we are going to treat this 3 minus x as a constant. So that's equal to 3 minus x. Here we have y minus 1 over 2 y squared. And here we have integration limits from 0 to x. But still here we have dx, which is equal to integral from 0 to 1. 1 is 0. Every term contains y. That's was equal to 0. Y is equal to x. So here we have 3 minus x times x minus 1 over 2 x squared dx. Now, if you just simplify and integrated with respect to x, here we have 0 to 1, 3 times x, here we have 3x minus x squared minus 1 over 2 x squared, that's equal to minus 3 over 2 x squared, and here we have dx. So which is equal to, how to integrate, it's just our usual function, so that's equal to 3 over 2 x squared minus 1 over 2 x cubed. And here we have integration limits from 0 to 1. 1 it is 0, that's equal to 0. 1 it is 1, that's equal to 3 over 2 minus 1 over 2, that's equal to, what is it? Just 1. Okay, let me just duplicate this because I need more space. Okay, we have space here, no problem. How about if we just change the order of integration here, first with respect to x, then y. At the time, again, the second one is, let's say this volume will be equal to, again, we are just integrating this over this region. Okay, this one is 1, and this one is also, it is 1. So the equation of this line is y is equal to x. How about first y and x? Here we have our function is 3 minus x minus y. 3 minus x minus y. In the first case, we integrated with respect to y, but now I want to integrate first with respect to x, then it is y. Okay, so now actually y, it is changing from 0 to 1. As see here, the 0 to 1 it contains all the horizontal lines that you draw parallel to the x-axis. So actual y is changing from 0 to 1. And how about x-axis? To do this one, to find this, the integration limits for x-axis. So just you need to draw a line that is parallel to the x-axis. So you see here, it enters the region here and exits here, right? So it's entering part, that is x is equal to y. How about exiting part? This x is equal to 1. So this x is changing from y to 1. Okay. Okay. So let's continue. Equals integral from 0 to 1. So if we integrate this 3 minus x minus y with respect to x, that means that we're going to treat this 3 and y as a constant, right? So here we have 3 minus y, and here we have x minus 1 over 2 x squared. So the integral is changing from y to 1. And here we have dy, which is equal to integral from 0 to 1. When it is 1, okay, when it is 1, here we have 3 minus y minus 1 over 2, right? Minus, when it is y, here we have 3 minus y, and here we have y, and actually, I need to put here like this, 3 minus y times y minus 1 over 2 y squared. And here we have dy. Okay, because integration limits, they are not constant numbers, they are variables. That's equal to, further simplify this, integral from 0 to 1. And here we have 3 minus half, that is 5 over 2 minus y, minus, and here we have 3 times y is 3y, so minus 3y, minus y minus y minus y squared, and minus 1 over 2y squared minus 3 over y to square. With this minus, it is plus 3 over 2y squared, and here we have dy. And I can simplify further. Here we have integral from 0 to 1, 5 over 2 minus y minus 3y, that is minus 4y, and plus 3 over 2y squared dy. So now if you just integrate this, we have here 5 over 2y minus 2y squared plus 1 over 2y cubed. And here we have integration limits from 0 to 1. When it is 0, that's equal to 0. When it is 1, here we have 5 over 2 minus 2 plus 1 over 2, which is equal to 1. And the same result with the previous one. So that's how we change the order of integration. Of course, here you don't have any general rule in which order we have to calculate, but sometimes you will see that, of course, if you integrate with respect to y, you may face some kind of trouble. Okay, so immediately what happens here, maybe your function gets more and more complicated, or even sometimes it becomes impossible. So immediately we have to change the order of integration and try this again. Of course, still we cannot guarantee that every integral can be calculated. Sometimes it is not possible because we cannot integrate this. At that time, we will just use numerical method to evaluate this integral, double integral. Okay, one example for this. Calculate this double integral over the region R of sine of x over x dA, where R is the triangle in the xy plane bounded by the x-axis and the line y equals x and the line x equals y. It is just the same region that we have just used here. So we are going to integrate this over this region again. So that is our y-axis, this is our x-axis, and this one is y equals x, and this point is 1, and also this point is 1. So our integration region is this. Okay, we are going to integrate this over this region. So now, okay, first number one, what happens if I integrate this first with respect to x and after that y? Okay, so here we have integral and integral, and this point is 1 and 1, right? Y is changing from 0 to 1. And how about the x? We have just used this one, right? It enters here and x is here. So x is changing from y to 1. And now here we have sine of x over x. So here we have dx and dy. Okay, so now if you try to integrate the sine of x over x dx, right? Just integrate. It's not possible to integrate this because we don't have any elementary function. So that when you integrate this, we get that function. Okay, that's why this is, what is it? Kind of troublesome here. So what happens if I just change the order of integration here? The second one is first respect to y, then x. So this y, for x is changing from 0 to 1. How about our y? If you draw a vertical line, it enters here and x is here, right? Our y is changing from 0 to x. So here we have sine of x over x. So here we have dy and dx. So if you evaluate this, the sine of x over x with respect to y is just a constant number. So that's equal to from 0 to 1. Here we have sine of x over x times here we have y, which is changing from 0 to x. And here we have dx. And that is equal to 0 to 1. When y is equal to 0, 0 times sine of x over x, that's equal to 0. When it is x, here we have x, right? X over x is gone. What is left here? Only sine of x. So here we have x, which is equal to minus cosine of x, changing from 0 to 1. So that is minus cosine of 1 minus cosine of 0, which is equal to 1 minus cosine of 1. Okay, then approximately we can evaluate this. If you have a calculator, calculator here, huh? Okay. So that is approximately equal to 0.46. Okay. Now, let's talk about finding limits of integration. We now give a procedure for finding the limits of integration. We have already done this. I have already explained this, but one more time, just a kind of official, okay, how we are going to do this. So that applies for many regions in the plane. Regions that are more complicated and for which this procedure fails can often be split up into pieces on which the procedure works. That means that sometimes if the integration region is so complicated, soon actually we'll have a look at the properties of this double integral. We can just divide this into some, what is it, simpler regions so that it makes your integration process much easier and possible. Number one, using vertical cross sections. When faced with evaluating this double integral over the region R of f, integrating with first respect to y and then respect to x, do the following 3 steps. Okay, number one, we have to sketch the region of integration and label the bounding curves. And suppose that our region is given by these two equations, x squared plus y squared, that's equal to 1, and x plus y is equal to 1. Okay, so this x squared plus y squared is equal to 1. If you draw this, it's a circle, right? And x plus y equals 1, we know that it is just a straight line. So they meet each other at y-axis at 1 and x-axis at 1. Okay, so this blue region, they are intersection points, so they form this region. Now we are going to integrate our function over this region. Okay, number one, maybe with here first we want to integrate with respect to y, right? So y means that if you draw a line that is parallel to the y-axis, you will see that actually our line enters the region here and exits the line here, that means the region. So as you see here, they are variables, they're not constant functions. So enters at what? Actually, the equation of this line, actually y is a function of x here, 1 minus x. and exist this region at this point that is given by y equals square root of 1 minus x squared, because we know that in the first quadrant that x squared plus y squared equals 1, right? Y coordinate should be equal to 0. That's why we are just ignoring the negative sign. So now we know the integration limits for y, right, is changing from 1 minus x to square root of 1 minus x squared. So now we have to choose two lines actually that covers or that contains all these vertical lines. So what is it? When actually x changes from 0 to 1, right, it covers or contains all of these vertical lines. So to find the x limits of integration, choose x limits that include all the vertical lines through R. So that is smallest x is x equals 0. If you move a little bit to the left, it does not contain any vertical line, or to the right of 1 also it does not. So actually if x changes from 0 to 1, that actually includes all these vertical lines. Then the integral shown here is double integral over r f of x y dA. That's equal to x is changing from 0 to 1, and our y is changing from 1 minus x to 1 minus x squared. Usually from the integral dy here is here, right? We know that the first integral is about y. That's why we don't have to write y. It's just for explanation purpose. Okay, the second one is using horizontal cross section. Okay, to evaluate the same double integral as an iterated integral with the order of integration reverse. Use horizontal lines instead of vertical lines in step 2 and step 3. That means that now first we are going to integrate this with respect to x, right? So we have to draw a line that is parallel to the x-axis. And again, just mark where does it enter the region and where does it exit the region. See here, it enters the region here and exits the region here. So that means that x is changing from 1 minus y to square root of 1 minus y squared. And that's why here we have x is changing from 1 minus y to 1 minus y squared. And how about y? When y changes from 0 to 1, it includes all of these horizontal lines. Example 3. Sketch the region of integration for the integral and write an equivalent integral with the order of integration reversed. So solution. So I see here this dx, right? X is changing from 0 to 2. So here our coordinate system, this one is x and this one is y. Our x is changing from 0 to 2. This is 0 and this is 1 and this one is 2. And how about y? Y is changing from y1 equals x squared to y2 is equal to 2x. And we know that in the first quadrant, x squared is just one branch of parabola. So parabola, when it is, let's say this 1 and this one is 2, this one is 4, not drawn to scale. So it is, let me just draw here, that is our parabola. This. Okay. Now, how about y2 equals 2x? It is a straight line. So that is a straight line here. If you just draw this, it passed through the origin. Okay, it actually meets the parabola here. So this point is 2 and 4. Okay, so our integration region is this. We are integrating our function over this region. So now here, first with respect to y, right? How can we change the order of integration here? So here we need to have integral and integral. Here we have 4x plus 2. And here we have dx and dy. Now, as see here, first, if we just dx, right, to find the integration limits for dx, we need to draw a line that is parallel to, what is it? X-axis. So if I draw any horizontal line parallel to the x-axis, it enters the region here and exits the region here. So this entering part, right, that is our straight line. So y is equal to 2x. From here, x is equal to y over 2. And how about the exiting part? This exiting part is y is equal to x squared. We know that y is positive. From here, x is equal to square root of y. So now at the time, you can just write the limits. So the y is changing from 0 to 4. And how about this x? X is changing from y over 2 to square root of y. Okay. And actually, these two integrals, they give us the same results. It's a, and also it gives us a. This is how we change the order of integration. Properties of double integrals. Like single integrals, double integrals of continuous functions have algebraic properties that are useful in computations and applications that actually speeds up our computation. Just here, this suppose that we are given the region R, we can just split this into two parts, which actually, if it makes our integration easier, otherwise it doesn't make sense. Let's say R is a union of R1 and R2. Now from here, this double integral over R is equal to double integral over R1 plus double integral over R2. So this if f and g are continuous on the bounded region R, then the following properties hold. These are very similar to our properties of, what is it, single integrals. So double integral multiplied, our function multiplied by constant number c, we can just take this out of this double integral. And the sum and difference, if you add two functions or subtract and integrate this, it's the same as first integrate and add them up or subtract them. In domination, if you are integrating, okay, a non-negative function, also the result will be non-negative, because after all, we're just summing up these partial sums, right? I mean, the Riemann sum. Okay, these are the properties of double integral. So we have one question left, and after that, we'll have a break. Find the volume of the wedge-like solid that lies beneath the surface, z equals 16 minus x squared minus y squared, and above the region R, bounded by the curve y equals 2 times square root of x, and the line for x minus 2. So first, if you draw this region, this one is x, this one is y. Okay, so what is our y equals 2 times square root of x? This curve is something like this. Okay, and how about for x minus 2, when x equals 2, not x equals 2, when x equals 1 over 2, that's equal to 0. So here, actually, that one is 1, they meet each other. So this one is 1 over 2. It's a straight line, so it is this. Okay, so this is the region that we are going to integrate our function. Okay, this is our region. Now, actually, if you integrate this first with respect to y, if you draw lines, for example, in the first part, it may change from 0 to this curve, right? But the other part, as you see here, it is changing from this point to this point. So it was a bit challenging, or it actually involves two different regions. But instead, here, we better integrate this first with respect to x. It just enters here and exits here, right? And after that, with respect to y. So that's why here, before you start integrating your function, you have to make a decision which order is much better, shorter, and faster. So here, solution. What is it? So this, let's say it is v, that is double integral. And first, y is changing. What is this point? It is when it is 1, it is 2, right? So y is changing from 0 to 2. So y is changing from 0 to 2. And how about x? It enters here and exits here, right? The entering part from here, y equals 2 times square root of x. So from here, what is x? X equals y over 2 squared. So it is changing from y squared over 4. And exiting here, if you express this y equals 4x minus 2, express x in terms of y. So x is equal to y plus 2 over 4. So here we have y plus 2 over 4. Now here we have our function 16 minus x squared minus y squared, first with respect to x, then with respect to y. Equals, here the first integral 0 to 2. So with respect to x, here we have 16 minus y squared, and here we have x minus x squared. X squared is 1 over 3 x cubed. So here we have integration limits. from y squared over 4 to y plus 2 over 4. And here we have dy. So now if you substitute for x here, then we'll get equals integral from 0 to 2. The first part, here we have 16 minus y squared. What is x? X is y plus 2 over 4 times minus 1 over 3 times y plus 2 over 4 cubed. Okay, that's the first part. Minus, and how about the second part? Here we have 16 minus y squared times x. X is y squared over 4. And let me just erase this. I don't need it anymore. And minus 1 over 3 times x cubed. X cubed is y squared over 4 over 4. And here it is cubed. Close it. Okay. And the integral here we have dy. Now, if you just expand this, evaluate this, actually on purpose, given that also we may have some long integrals, okay, it's a bit quite long, takes time, and we can evaluate this, and just evaluate this integral here, we will have the final answer is, after simplifying this, here we have 191 y over 24 plus 63 y squared over 32 minus 145 y cubed over 96 and minus 49 y to the power of 4 over, what is this, 768, and plus y to the power of 4 over 20 and plus y to the power of 7 over 1344. And integration limits are from 0 to 2, which is equal to 20,803 over, okay, 1680. And that's approximately equal to 12.4. Because inside this brackets actually still but just simple algebraic manipulation, okay? And of course, if you have practiced a lot of questions, you can do this very, very fast, but maybe even the class we can discuss this if there's any problem. On purpose, actually, it's given here that sometimes our integral may involve a long calculation. Guys, that's all for this section. Let's have rest for, let's say, a few minutes. I will continue at 4 o'clock, and our next class will be a bit shorter, maybe 20 minutes, okay? Then I will finish the class. See you after 15 minutes.